In this lecture series, we'll learn about alkenes. And in particular, we'll learn about their stereochemistry and their reactivity toward electrophiles. Remember that an alkene is an organic compound that has a carbon-carbon double bond. And because there is no rotation around these double bonds, when we have a group or a substituent on each carbon of the alkene, when we have a 1,2 disubstituted alkene, there are two possible arrangements of those groups. There are two possible stereoisomers of 1,2 disubstituted alkenes. And to illustrate this, we'll look at 2-butene. In 2-butene, each carbon of the alkene is bound to one methyl group and one hydrogen. And that means that the two methyl groups can be on the same side of the alkene or on opposite sides of the alkene. And when we're referring to the sides of the alkene, we're really imagining drawing a line that follows that pi bond. When the two methyl groups are on the same side of the alkene, this is the cis stereoisomer. And when the two methyl groups are on opposite sides of the alkene, it's the trans stereoisomer. And when we name alkenes, we include the cis or trans designation at the beginning of the name, followed by a hyphen. So on the left here we have cis 2-butene, and on the right we have trans 2-butene. The cis and trans designations only apply to 1,2 disubstituted alkenes. To identify the stereochemistry of tri- and tetrasubstituted alkenes, we use E and Z nomenclature. And this naming system relies on the Kahn-Ingold-Prelog priority rules that we learned for determining the R and S designation of chiral centers. On this slide, we'll walk through an example of how we apply those priorities to alkenes. First, we rank the two groups attached to each carbon. And we want to be sure to look at each carbon independently. In our example, starting with the carbon on the left, it's bound to a chlorine and a hydrogen. The chlorine is a higher priority than hydrogen, so chlorine is denoted 1 and hydrogen is denoted 2. The other alkene carbon on the right is bound to a methyl group and an ethyl group. The ethyl is the higher priority than the methyl, so ethyl is denoted as 1 and methyl as 2. Then we look to see if the two high priority groups on each carbon are on the same side or different sides of the alkene. If they're on the same side, then the alkene is the Z stereoisomer. And if they're on opposite sides, the alkene is the E stereoisomer. So in our example, the two high priority groups are on opposite sides of the alkene, so this is the E stereoisomer. Finally, we include the E or Z designation in italics and in parentheses at the beginning of the name. This compound is named E, 1-chloro-2-methylbutene. And one final note here is to acknowledge that the E and Z isomers are stereoisomers. They have the same connectivity of atoms, but a different arrangement of those atoms in space. Okay, let's pause for a concept check. Take a minute to name the two alkenes shown below, and of course the name should include the appropriate E and Z designations. I'll start with the compound on the left and first determine the E and Z designations. This alkene has only one group on it. It's a monosubstituted alkene, and so it has no E or Z or cis or trans designation. It has no stereochemistry. The other alkene, though, has three different groups on it, so it will have an E or Z designation. And to determine that designation, we need to prioritize the groups on each carbon. On the left carbon, the methyl group is a higher priority than the hydrogen. And on the right carbon, the alkene is a higher priority than the methyl. The two high priority groups are on opposite sides of the alkene. So this is an E isomer. Now we need to name the alkene. And to do that, we number our chain, beginning at the end nearest the alkene. The parent here is 5 carbons long, a pentane, and it has 2 alkenes. So we call it a pentadiene. and the alkenes are in 1 and 3 positions, so it's a 1,3 pentadiene. Then we name and number the substituents or groups on the chain. Here we have only one group, a 3-methyl. And finally, we denote the stereochemistry of the alkene with an E in parentheses at the beginning of the name, followed by a hyphen. So this first compound is named E, 3-methyl, 1,3 pentadiene. In the second example, there is only one of the 2 alkenes with stereochemistry. On the carbon on the right, the bromine is a higher priority than the hydrogen. On the carbon on the left, the alkene is a higher priority than the isopropyl group. So this is also an E stereoisomer. To name the compound, we find the parent chain and number it from the end closest to the alkene. In this case, both ends have an alkene, so we number from the end with the most substituents, and that's the side with the bromine on it. This is a 1,3 butadiene. Now let's look at the groups. We have a bromine on carbon 1 and an isopropyl group on carbon 2. Our stereochemistry is E, so the full name is E, 1-bromo, 2-isopropyl, 1,3 butadiene. One final piece to look at before we end this lecture video is the relative stabilities of different alkenes. Alkene stability increases as the number of alkyl groups on the carbon-carbon double bond increases. That means that tetrasubstituted alkenes are the most stable alkenes, followed by trisubstituted alkenes, then disubstituted alkenes, then monosubstituted alkenes, and then finally ethylene is the least stable alkene. Within disubstituted alkenes, trans alkenes are more stable than cis alkenes. And the stabilization that arises from increased substitution comes in part from an orbital interaction that we call hyperconjugation. And all this means is that there's a stabilizing interaction between the anti-bonding orbital of the carbon-carbon pi bond and the adjacent CH sigma bond.